Enterprise AI teams have moved past the pilot phase. They are now migrating high-volume workflows into live production environments. But successful deployment has triggered a contradiction. As these systems scale, cloud bills spike, and the business sees eroding gross margins. When facing cost friction, teams rely on a standard response. They request more GPU capacity and push for higher quotas to maintain performance. Attempting to solve a software scaling issue with hardware expansion is mathematically flawed. Physical capacity cannot keep pace with the exponential demand of production inference without breaking the budget. Enterprise AI cost overruns are typically routing failures misidentified as compute shortages. Treating these failures as hardware problems ensures inference costs will scale linearly with usage. At that point, the unit economics are broken. Margin erosion happens because of how requests are managed. Distinct workloads, support, search, and code gen, all funnel into a single pathway. Without intervention, inference follows the path of least resistance. It creates massive single cloud and single model dependencies, enforcing maximum precision settings universally. This setup creates massive operational waste. Basic summarization or asynchronous back-office tasks do not require maximum precision or premium GPUs. Over-provisioning like this creates a compounding tax. Across millions of daily API calls, the waste becomes truly significant. Without routing logic, the enterprise pays a premium rate for every inference, even when the task only requires a fraction of that intelligence. Financial leadership identifies this infrastructure failure through 2 rows on a quarterly infrastructure report: AI inference volume and cost per inference. Rising total cloud bills are expected. As volume increases, the total spend should go up. But the actual red flag is when the cost per inference remains static while the total workflow volume scales. Traditional SaaS economics are built on the idea that scaling volume should drive down unit costs through efficiency. If your cost per inference is flat, you are paying the same premium for the millionth request as you did for the first. By Q2 2026, CFOs will audit these lines to see if AI investments have actually contributed to gross margin. A static cost per inference metric is proof that an enterprise lacks an orchestration layer. This comparison shows why most enterprises cannot scale AI requests effectively. On the left, routing logic is trapped inside bespoke glue code. This logic is fragmented across disparate scripts, with each application team managing its own connections. Manual scripting fails at scale. It offers no cross-provider visibility and creates API chaos as different apps fight for quota. The system relies on tribal knowledge. Developers often hard-code specific model preferences that never get updated or optimized. Now look at the right side. This is a dedicated routing layer, acting as a centralized control plane. This broker layer sits between your internal demand and the available compute supply. It abstracts the complexity. Developers send requests to the router rather than individual APIs, and the layer decides the path. This establishes a single point of audit and control for every AI request leaving the enterprise environment. Decoupling volume from cost requires moving logic out of app silos and into a dedicated broker layer. The routing layer operates through policy as code. As a request enters, it passes through a series of filter gates. First, it evaluates the latency budget. It identifies which tasks require an immediate response and which can wait. The PII gate enforces data residency and jurisdiction rules, ensuring sensitive data stays within required boundaries. Of the hardware gate, the router identifies asynchronous workloads, such as batch processing tasks. These workloads are automatically redirected to cloud regions, where compute is currently cheapest. The router also evaluates required precision. It intentionally moves low-risk tasks to lower-tier hardware. This careful triage reserves premium GPU clusters for the small percentage of tasks that actually require low-latency intelligence. Policy-driven routing is the only architectural way to align compute spend with actual workload requirements. You can prove this inefficiency with a 48-hour pilot. This framework identifies the cost delta between your current defaults and a routed system. On day 1, select 3 production-like workloads, such as RAG search or support summarization. Run these identical workloads across 2 different models and 2 different cloud regions. On day 2, analyze the results. Measure the unit cost, latency, and output quality of each configuration. Compile these metrics into a 1-page report on the unit economics gap. This test consistently uncovers a cost spread greater than 40% without meaningful loss in quality. A 40% cost spread identifies the decision layer as the primary infrastructure bottleneck. Quantifying this waste forces a shift in strategy. It moves the focus from blind hardware expansion to strict routing discipline. Establishing an inference routing layer shifts negotiating leverage back to the enterprise. Scaling success requires the ability to deploy across multiple models and regions based on policy. It also provides the auditable logic necessary for compliance and future financial reviews. Strategic advantage in enterprise AI belongs to the teams that own the routing decision layer. Whoever owns the routing owns the economics.